Deep in the vast expanse of space, there exists something so strange, so unimaginably dense, that it defies everything we know about matter. Picture this: a single teaspoon of material, scooped from the heart of a neutron star, would weigh more than all the cars, buildings, and mountains on Earth combined. That's not science fiction. That's the staggering reality of these cosmic powerhouses, the remnants of massive stars that have collapsed under their own gravity. But here's the real mystery: what's hiding in their cores? What bizarre, otherworldly secrets lie buried beneath layers of matter crushed to its absolute limits? Today, we're embarking on a journey to the very edge of known physics, where the rules of our universe bend and twist into something unrecognizable. Neutron stars are more than just cosmic curiosities. They're natural laboratories, pushing matter to extremes we could never recreate on Earth. At their cores, conditions are so extreme that atoms themselves cease to exist. Protons and electrons are squeezed together until they merge, forming a sea of neutrons so dense it behaves like a single, gigantic atomic nucleus. But scientists suspect even stranger things lurk deeper within. Some theories suggest the core might contain exotic states of matter, like quark gluon plasma, a primordial soup that hasn't existed since the first moments after the Big Bang. Others speculate about hyperons, particles so rare they're almost mythical, or even stranger forms of matter that could rewrite the laws of physics as we know them. This isn't just about satisfying our curiosity. Unlocking the secrets of neutron star cores could answer some of the biggest questions in the universe. How does matter behave under infinite pressure? What happens when gravity becomes so strong it warps the very fabric of space-time? Could these stars hold clues about dark matter, black holes, or even the origins of the cosmos itself? By peering into these stellar enigmas, we're not just exploring distant objects, we're uncovering the fundamental truths that govern reality. So buckle up, because we're about to dive into one of the most thrilling frontiers of modern astrophysics, where every discovery has the power to change everything we thought we knew. To witness the birth of a neutron star is to watch one of the most violent and spectacular events in the cosmos, a supernova explosion. Picture a massive star, many times heavier than our Sun, burning through its fuel over millions of years. As it runs out of nuclear fuel, the outward pressure that once kept it stable vanishes, and gravity takes over in an instant. The star collapses catastrophically, its outer layers exploding outward in a blinding flash while the core implodes with unimaginable force. In less than a second, a city-sized remnant is all that remains, but this tiny object holds the mass of an entire star, squeezed into a sphere no wider than Manhattan. This collapse doesn't just shrink the star, it fundamentally transforms the very nature of matter. Under normal conditions, atoms are mostly empty space, with electrons orbiting a dense nucleus. But inside a neutron star, gravity is so intense that electrons are crushed into protons, transforming them into neutrons. The result: a bizarre, ultra-dense sea of neutrons packed so tightly that a single sugar cube's worth would weigh as much as a mountain. Yet even this extreme state might not be the final form of matter in the core. Some scientists believe the crushing pressures could break neutrons themselves apart, revealing even stranger substances like free-floating quarks or exotic particles that only exist under these impossible conditions. The mystery deepens when we consider how little we can directly observe about neutron star cores. These objects are so dense that light can't escape from their surfaces. Any radiation we detect comes from their outer layers or powerful magnetic fields. To study their hearts, astrophysicists must rely on indirect clues, like the way neutron stars spin, vibrate, or even collide with one another. Each observation peels back another layer of the puzzle, hinting at realities far stranger than we ever imagined. What we're learning doesn't just rewrite the story of these stars, it challenges our understanding of matter itself. The crust of a neutron star is like nothing you'd find on Earth, a surreal landscape where the familiar rules of matter break down spectacularly. Imagine atomic nuclei stripped of their electrons, squeezed so tightly together that they arrange themselves into a rigid crystalline lattice, like a cosmic ice sheet floating atop an ocean. But this isn't water beneath it. It's a neutron superfluid, a frictionless sea of particles flowing without resistance, defying everything we know about viscosity. Even here, in these outer layers, the physics is mind-bending. Yet this is just the surface of the mystery. As we venture deeper, the pressure mounts to levels so extreme that matter itself begins to unravel. The deeper we go, the stranger things become. Beneath the crust, gravity's relentless crush forces nuclei so close that they dissolve entirely, their protons and neutrons merging into a continuous, swirling mass. This is the inner crust, a twilight zone where matter transitions from recognizable atomic structures to a quantum soup. Here, neutron-rich postaphases might exist, named for their bizarre shapes: nuclear lasagna sheets, spaghetti strands, or even bubble-like formations, all sculpted by the competing forces of gravity and nuclear interactions. These structures aren't just theoretical quirks. They could explain why neutron stars occasionally starquake, cracking under unimaginable stress like tectonic plates, but on a cosmic scale. But the real enigma lies even deeper. Past the inner crust, the pressure becomes so intense that neutrons themselves might not survive. Some theories suggest they break apart into their constituent quarks, creating a swirling ocean of free-floating particles that haven't existed freely since the universe was a trillionth of a second old. Others propose the existence of Hyperons, exotic particles heavier than neutrons, laden with strange quarks, which could turn the core into a realm of unpredictable energy. And then there's the most radical idea of all, that the core might collapse into a singularity, a black hole in miniature, hidden beneath layers of degenerate matter. What makes this puzzle so tantalizing is how little we can observe directly. Neutron stars don't give up their secrets easily. Their cores are buried under miles of impossibly dense material, shielded from even the most advanced telescopes. Instead, scientists rely on subtle clues: the way these stars spin, how they emit gravitational waves during collisions, or even the precise timing of their pulsar signals. Each anomaly in these observations could be a breadcrumb, leading us closer to understanding what's truly happening at the heart of these cosmic anomalies. One thing's certain: whatever lies in the core doesn't just challenge our models of matter, it rewrites them. At the very center of a neutron star, where pressures reach levels 100 trillion times greater than Earth's atmosphere, the laws of physics as we know them begin to unravel. This is a realm where gravity doesn't just bend space-time, it shreds the very definition of matter. Under such extreme conditions, the familiar protons and neutrons that make up atoms may no longer hold their shape. Instead, they could dissolve into a swirling, seething ocean of quarks, the fundamental particles that normally stay locked inside them. Picture it like this: if a neutron is a tightly clenched fist, the core's unimaginable force might pry it open, releasing the individual fingers, the quarks, to move freely in a chaotic, primordial dance. This hypothetical state, known as quark matter, would be unlike anything we've ever observed. In ordinary matter, quarks are always confined, bound together by the strong nuclear force. But here, in the heart of a neutron star, they might break free, forming a quark gluon plasma, a state that hasn't existed since the universe was just microseconds old. Some theories even suggest this quark soup could crystallize into something even stranger, a color superconductor where quarks pair up in ways that defy conventional physics, creating a material with zero electrical resistance and properties we can barely comprehend. But quarks aren't the only players in this quantum drama. Deeper still, the core might host Hyperons, exotic particles studded with strange quarks, which are far heavier and more unstable than the quarks in everyday matter. These particles can't survive under normal conditions, but in the neutron star's core, they might become stable, weaving themselves into the fabric of this ultra-dense material. And if Hyperons exist there, they could dramatically alter how the star behaves, perhaps even explaining why some neutron stars seem slightly squishier than our models predict. Yet the most radical possibility is that the core doesn't stop at quarks or hyperons. Some physicists speculate that under such extreme pressures, matter might transform into an entirely new phase, one that blurs the line between a neutron star and a black hole. Could there be a tiny singularity hidden inside, a black hole so small it's stabilized by the surrounding matter? Or does the core become a fuzzy, quantum mechanical boundary where space-time itself becomes granular, like pixels on a screen? The answers could rewrite our understanding of reality. The challenge, of course, is that we can't just peer inside a neutron star to see what's happening. Instead, scientists rely on subtle clues like ripples in space-time from colliding neutron stars, or the way these stars occasionally hiccup in their rotation, emitting bursts of energy. Each observation is like a piece of a cosmic jigsaw puzzle, hinting at the surreal physics playing out in their cores. What we do know is this: the heart of a neutron star isn't just a curiosity. It's a window into the universe's most extreme secrets waiting to be unlocked. Among these mind-bending theories about neutron star cores, one stands out as both thrilling and unsettling: the strange matter hypothesis. Imagine a substance so stable, so indestructible, that it could rewrite the rules of the universe as we know it. This isn't just about exotic particles or extreme pressures. It's about a material that could, in theory, transform everything it comes into contact with. At its heart lies strange matter, a hypothetical state where quarks aren't just free but organized into an entirely new form, composed of up, down, and strange quarks. Unlike ordinary matter, where quarks are bound tightly inside protons and neutrons, strange matter could exist as a perfectly balanced, ultra-dense soup, more stable than even the atomic nuclei that make up our world. The implications are staggering. If strange matter exists in neutron star cores, it might not stay confined there. Under the right conditions, a single droplet of this substance could theoretically convert ordinary matter into strange matter upon contact, like a cosmic chain reaction. Picture a snowball effect where atoms, whether in a star, a planet, or even a spaceship, are rewritten at the most fundamental level. This idea, sometimes called the Strangelet scenario, sounds like something straight out of science fiction, but it's rooted in real quantum physics. The catch: no one knows if strange matter is stable enough to exist outside the insane pressures of a neutron star's core, or if it's just a fascinating mathematical possibility. What makes this hypothesis so compelling is how it bridges the gap between particle physics and cosmology. Strange quarks, which give strange matter its name, are heavier and rarer than the up and down quarks found in everyday matter. They typically appear only in high-energy collisions or decay almost instantly. But inside a neutron star, where gravity crushes matter beyond recognition, strange quarks could become the dominant players, creating a substance unlike anything else in the known universe. Some models suggest that if strange matter forms, it could explain why certain neutron stars seem slightly smaller or heavier than predicted. Their cores might have undergone this bizarre phase transition, collapsing into a denser, stranger state. Yet for all its intrigue, the strange matter hypothesis remains fiercely debated. Critics argue that the conditions needed to stabilize strange matter might be too extreme, even for neutron star cores. Others point out that if strange matter were truly stable, the universe should be full of it, yet we see no evidence of rogue strangelets floating through space. Then again, maybe that's a good thing. If strange matter does exist, and if it's as contagious as some theories suggest, the fact that we haven't encountered it might be the universe's way of protecting us from a phenomenon that could quite literally rewrite reality. The search for answers isn't just academic. Collisions between neutron stars, detected through gravitational waves and bursts of radiation, could be our best chance to spot the fingerprints of strange matter. These cosmic crashes release unimaginable energy, possibly ejecting traces of exotic material into space. If even a speck of strange matter survived such an event, its properties could reveal whether this hypothesis is a revolutionary truth or just a captivating dead end. For now, the mystery lingers, reminding us that the universe's most extreme laboratories, neutron star cores, still hold secrets capable of transforming our understanding of existence itself. Deep inside a neutron star, where matter is squeezed beyond recognition, protons and neutrons might not just exist. They could be performing a quantum ballet unlike anything in the visible universe. Picture protons, those positively charged particles that normally repel each other, suddenly teaming up in perfect harmony, forming a superconductor that lets electricity flow without resistance. Meanwhile, the neutrons surrounding them could be slipping past one another like a ghostly, frictionless liquid, a superfluid capable of swirling endlessly without losing energy. This bizarre partnership isn't just theoretical. It could be the key to unraveling two of neutron stars' most puzzling behaviors: their monstrous magnetic fields and their mysterious rotational glitches. Take the magnetic fields first. Neutron stars are cosmic magnets on steroids, with fields trillions of times stronger than Earth's. If protons in the core form a superconductor, their paired-up movements could generate colossal electric currents, amplifying the star's magnetic field to unimaginable levels. It's like a dynamo on overdrive where charged particles whirl in sync, creating a magnetic powerhouse that can light up entire galaxies with pulsar beams. But here's where it gets even stranger. Superconductors expel magnetic fields, a phenomenon called the Meissner effect. So why don't neutron stars cancel out their own magnetism? The answer might lie in chaotic vortices, tiny whirlpools of magnetic flux that get trapped in the superconducting soup, creating a messy, dynamic interplay between superconductivity and magnetism that defies simple explanation. Then there are the glitches, those sudden, unpredictable jumps in a neutron star's rotation. One moment, a pulsar spin is as regular as a clock. The next, it speeds up by a fraction of a second, as if the universe hit the fast-forward button. The culprit, superfluidity. In this frictionless state, neutrons in the inner crust or core can move independently of the star's rigid outer layers. Normally, they rotate in sync, but as the star gradually slows down over time, the superfluid might resist the slowdown, storing angular momentum like a wound-up spring. When the tension becomes too much, the superfluid's vortices suddenly reorganize, transferring a burst of energy to the crust, and voila, a glitch occurs. It's like a figure skater pulling their arms in mid-spin, but on a cosmic scale, with forces so extreme they warp the very fabric of matter. Yet these phenomena aren't just cosmic curiosities, they're clues. The way a neutron star's magnetic field evolves, or how often it glitches, could reveal the hidden structure of its core. If protons superconduct, does their behavior change at different depths? Could there be layers where superconductivity breaks down, creating zones of turbulence? And what happens when superfluids interact with those hypothesized quark matter cores? Each observation peels back another layer, hinting at a reality far more intricate than our models predict. The wildest part, we're only beginning to scratch the surface. Every glitch, every magnetic hiccup is a whisper from the heart of a neutron star, urging us to listen closer. Neutron stars shouldn't exist, at least not the way we've observed them. According to our best models, these cosmic remnants should collapse into black holes if they grow too massive. Yet astronomers keep finding ones that defy this limit, tipping the scales at over 2 times the mass of our Sun. How is that possible? The answer might lie in the unexplored physics of their cores. If neutron stars harbor exotic forms of matter, like free quarks, hyperons, or even that theoretical strange matter, these bizarre substances could provide the extra pressure needed to counteract gravity's relentless crush, propping up stars that should have collapsed long ago. This isn't just a numbers game. Every unexpectedly heavy neutron star is a crack in our understanding of matter itself. Take the record holder, PSR J0740 plus 6620, a pulsar so dense it clocks in at nearly 2.1 solar masses. If this star were made only of neutrons, the pressure at its core should have triggered a catastrophic collapse. The fact that it hasn't suggests something far stranger is at work. Perhaps a core where neutrons dissolve into a soup of quarks, generating enough outward force to keep gravity at bay. Or maybe hyperons, those exotic particles laced with strange quarks, are jostling in the mix, altering the equation in ways we haven't yet imagined. To unravel this puzzle, scientists turn to 2 extraordinary tools: gravitational wave detectors and X-ray telescopes. When neutron stars collide, the resulting ripples in space-time captured by observatories like LIGO and Virgo carry fingerprints of their internal structure. A heavier star might deform differently during a collision, leaving subtle clues in the gravitational wave signal about whether its core is pure neutrons or something more exotic. Meanwhile, X-ray telescopes like NICER measure the star's sizes by studying how their intense gravity bends the light emitted from their surfaces. A smaller, heavier star points to denser, stiffer matter in its core, possibly hinting at quark matter's presence. But the most tantalizing hints come from the stars themselves. Some neutron stars occasionally glitch, suddenly spinning faster after years of gradual slowdown. These hiccups could be the core's exotic matter rebelling, superfluid neutrons reorganizing, or quark vortices snapping into new configurations. Even their cooling rates tell a story. Neutron stars with hyperon-rich cores might chill faster, as these particles can carry away heat more efficiently than ordinary neutrons. Every anomaly, every deviation from expectations, is a breadcrumb leading us closer to the truth. What's at stake isn't just academic. If neutron stars can grow heavier than we thought, it reshapes our understanding of where black holes begin. It challenges the limits of quantum physics, pushing us to ask, at what point does matter stop being matter? Each discovery peels back another layer, revealing a universe far stranger and more wonderful than we ever dreamed. Hyperons might be the universe's heavyweight champions of particle physics, exotic, unstable, and almost mythical under normal conditions. But inside a neutron star's core, where gravity crushes matter to unimaginable densities, these bizarre particles could become stable, rewriting the rules of what's possible. Imagine a proton or neutron, but with an extra quark, a strange quark, tucked inside, making it far heavier and more unstable. These are hyperons, and their very existence in neutron stars could solve some mysteries while creating others. The puzzle begins with pressure. As you dive deeper into a neutron star, the crushing weight forces particles to pack together tighter than anywhere else in the universe. At some point, ordinary neutrons might not be enough to withstand the squeeze. That's where hyperons could step in, forming naturally under these extreme conditions like cosmic pressure valves. But there's a catch. Hyperons interact differently than neutrons. They're softer, less resistant to compression. If too many of them appear in the core, the entire star could lose its structural integrity, collapsing under its own weight long before reaching the massive sizes we've observed. Yet here's the contradiction. Astronomers keep finding neutron stars that defy this logic. Stars like Pulsar J0740 plus 6,620, with masses over twice that of our Sun, shouldn't exist if their cores were full of hyperons. Their sheer bulk suggests something stiffer, something that can push back against gravity's relentless crush. So how do we reconcile these two ideas? One possibility is that hyperons exist, but not in the way we expect. Maybe they cluster in certain layers of the core, creating pockets of softness without destabilizing the entire star. Or perhaps another force, like the strong nuclear interaction between hyperons, kicks in under extreme pressure, stiffening the core unexpectedly. Then there's the quark factor. If hyperons share space with free-floating quarks in the core, their combined behavior might strike a delicate balance. Quark matter, especially in a superconducting state, could provide the extra rigidity needed to support the star's weight, while hyperons add complexity to the mix. It's like building a skyscraper with both steel and rubber. The steel keeps it standing, while the rubber absorbs shocks, preventing collapse. The stakes here are enormous. If hyperons do exist in neutron star cores, they could be our window into understanding the strong nuclear force, one of the universe's fundamental interactions, under conditions we can't replicate on Earth. But if they don't, or if their effects are cancelled out by even stranger physics, we might need to rethink our models entirely. Every gravitational wave from a neutron star collision, every glitch in a pulsar spin could be hiding clues. The answer isn't just about hyperons, it's about uncovering the universe's deepest secrets, one crushing discovery at a time. Could neutron stars be hiding an even stranger identity? Some might not be neutron stars at all, but quark stars, objects so extreme that their entire core has melted into a sea of free-floating quarks. This isn't just theoretical speculation. Take 3C58, a pulsar left behind by a supernova observed in the year 1181. Unlike most neutron stars, which cool gradually over millennia, 3C58 has lost heat far faster than expected, as if its core is conducting energy in a way ordinary neutron matter can't explain. The culprit, a quark matter core, where the absence of neutron-rich layers allows heat to escape more efficiently, like water flowing through a sieve instead of a sponge. The idea of quark stars sits in a tantalizing gray zone between neutron stars and black holes. If a neutron star's core crosses a critical threshold of density and pressure, it might not just harbor pockets of quark matter, it could transform entirely, like ice melting into water. In this state, the star's neutrons would dissolve completely, their quarks unshackled from their usual three particle groups and free to move independently. The result, an ultra-dense object where the entire interior is a swirling ocean of quarks. possibly with a thin crust of normal matter clinging to its surface. These hypothetical stars wouldn't just be hotter or colder, they'd operate by different rules altogether, with properties that could explain why some cosmic oddities defy classification. Yet proving quark stars exist is a monumental challenge. Without a telescope capable of peering directly into a neutron star's heart, scientists rely on indirect fingerprints like cooling rates, spin behavior, or gravitational wave signals. Some candidates, like XTJ 1739-285, have exhibited spin speeds so dizzying they approach the theoretical limit for neutron stars, suggesting a stiffer, denser interior, exactly what quark matter would provide. Others emit X-ray bursts with energy patterns that don't quite match predictions for pure neutron cores. Even their sizes could be a clue. Quark stars might be slightly smaller than neutron stars of the same mass, their quark-packed cores squeezing tighter under pressure. But the story isn't so simple. Critics argue that rapid cooling or fast spins could have other explanations, like unusually strong magnetic fields or residual heat from formation. And if quark stars are real, why haven't we found more unambiguous examples? The answer might lie in the fine line between stability and collapse. A quark star could be a fleeting phase, a neutron star's core teetering on the edge of becoming something else, perhaps lasting only centuries before transitioning into a black hole. Or maybe we're seeing them all along, mistaking them for ordinary neutron stars because their external signatures are too subtle to distinguish. The hunt for quark stars is more than a cosmic treasure hunt. It's a test of quantum physics at its most extreme. If they exist, they'd prove that matter can reach densities beyond even neutron degeneracy, unlocking states that haven't existed since the universe's first microseconds. Each candidate, each anomalous observation brings us closer to answering a profound question. Are we looking at neutron stars with strange hearts, or entirely new celestial objects hiding in plain sight? The universe, as always, keeps its most dazzling secrets under layers of mystery. Phase transitions inside a neutron star's core aren't as simple as ice melting into water. They're cosmic alchemy on an unimaginable scale. Picture matter so compressed that it flickers between states like a quantum chameleon, shifting from a sea of neutrons to a bubbling quark soup, or even crystallizing into exotic forms that defy ordinary physics. These transitions aren't just passive changes, they're energetic events capable of unleashing bursts of energy that ripple through the star, potentially triggering starquakes, magnetic field shifts, or even abrupt changes in rotation. But how do we detect such hidden transformations from light years away? One clue lies in the star's cooling rate. When matter undergoes a phase transition, say, from neutrons to quark gluon plasma, it releases latent heat, like steam condensing into water droplets. If a neutron star suddenly cools faster than expected, it could signal that its core has crossed a critical threshold, reorganizing into a denser, more efficient heat conductor. The Cassiopeia, a supernova remnant, offers a tantalizing hint. Its neutron star cooled by 4% in just a decade, a drop so sharp some theorists argue it's evidence of a superconducting quark core forming beneath the surface. Then there are the starquakes, violent cracks in the neutron star's crust that release energy equivalent to a magnitude 32 earthquake. These could be cosmic echoes of phase transitions deep within. As the core's matter reorganizes, it might abruptly shrink or expand, stressing the rigid crust above until it fractures. In 2007, astronomers observed a Magnetar, a highly magnetic neutron star, emit a flare so bright it briefly outshone our entire galaxy. The leading explanation, a catastrophic starquake possibly triggered by a phase shift in its core, releasing pent-up energy like a pressure cooker exploding. But perhaps the most dramatic signatures come from gravitational waves. When neutron stars collide, their cores are squeezed to even more extreme densities, potentially inducing rapid phase transitions. These shifts would distort the star's shape, leaving faint ripples in space-time detectable by observatories like LIGO. In 2017, the collision of two neutron stars, GW 170,817, sent gravitational waves and gamma rays across the universe. While the data didn't confirm quark matter outright, subtle anomalies in the signal left room for speculation. Future collisions might reveal clearer fingerprints of phase transitions, like a sudden stiffening of the merged core or an unexpected delay in its collapse into a black hole. The challenge is separating these signals from other cosmic noise. A neutron star's magnetic field, rotation, or even accretion of nearby material can mimic phase transition effects. That's why astronomers combine multiple observations, X-ray spectra, timing glitches, neutrino emissions, to piece together the core's hidden dynamics. Each dataset is like a fragment of a coded message, and phase transitions might be the key to deciphering it. If we can crack that code, we won't just solve a stellar mystery, we'll glimpse the universe's most extreme physics in action. The boundary between neutron stars and black holes isn't just a line in the sand, it's a cosmic tightrope, where matter teeters on the edge of existence. On one side, neutron stars push the limits of density, cramming more mass than our sun into a sphere the size of a city. On the other, black holes cross the point of no return, where gravity wins so completely that not even light can escape. But what happens in between? Could there be a secret third act where a neutron star's core collapses into something stranger than either? The tipping point comes down to mass. Current models suggest that once a neutron star surpasses about 2 to 3 times the mass of our sun, it should collapse into a black hole, but nature rarely follows tidy rules. Some neutron stars flirt dangerously close to this limit, like Pulsar J0740 plus 6620, which weighs in at 2.1 solar masses yet shows no signs of collapsing. This raises a tantalizing possibility. What if, instead of instantly becoming a black hole, the core undergoes a radical transformation first? Picture a neutron star so heavy that its neutrons break apart entirely, dissolving into a sea of quarks. This quark star, if it exists, would be denser than a neutron star but not quite a black hole, a fleeting intermediary where matter exists in a state we've never directly observed. Then there's the wild card strange matter. If the core's quarks rearrange into strange matter, a substance theoretically more stable than ordinary atomic nuclei, the star might resist collapsing even at higher masses. It's like building a house of cards that somehow holds firm under impossible weight. But if strange matter is real and contagious, a single neutron star's transformation could trigger a chain reaction, rewriting the fabric of nearby matter in ways we can't yet predict. The stakes of this mystery go beyond classification. When two neutron stars collide, their merged remnant could briefly exist in this ambiguous zone, hovering between neutron star and black hole before fate decides its outcome. Gravitational wave detectors like LIGO might catch these moments, listening for the telltale ripples of a core rebelling against collapse. A slight delay in the formation of a black hole, or an unexpected spike in brightness, could hint at an intermediate state, a cosmic stepping stone between the known and the unknown. What makes this search so urgent is how it challenges our understanding of gravity itself. Einstein's theory predicts black holes as inevitable endpoints, but quantum mechanics whispers alternatives: exotic stars, quark matter, or even stranger entities that defy both. Every neutron star skirting the edge of collapse is a test case, a natural experiment probing the universe's most extreme physics. The answer won't just redefine compact objects. It could reveal entirely new chapters in the story of matter, gravity, and the universe's hidden possibilities. Magnetars stand as the universe's ultimate magnetic monsters, neutron stars with fields so powerful they could strip the data from every credit card on Earth from halfway across the galaxy. These cosmic powerhouses don't just bend magnetic fields, they shatter our understanding of how such extreme forces are even possible. But here's the twist. Their magnetic fury might originate deep within their cores, where matter exists in states we can barely comprehend. The connection between a neutron star's hidden heart and its magnetic rage could rewrite everything we know about these celestial anomalies. At the surface, magnetars unleash magnetic fields 1,000 trillion times stronger than Earth's, capable of twisting atoms into distorted shapes. But the real engine of this chaos likely lies beneath. Picture the core as a swirling dynamo where superconducting protons paired up and moving in perfect sync generate electric currents on a cosmic scale. These currents, amplified by the star's rapid rotation, could be the source of those apocalyptic magnetic fields. Yet this isn't just a simple generator. If the core contains exotic matter like quark, gluon, plasma, or hyperons, their unique properties might supercharge the process, creating magnetic loops and knots far more complex than anything our physics predicts. The clues lie in magnetar outbursts. Sudden, violent eruptions of X-rays and gamma rays that light up the cosmos like flares. In 2004, a magnetar 50,000 light-years away released a burst so powerful it temporarily ionized Earth's upper atmosphere. Scientists suspect these explosions occur when the star's crust, strained by twisting magnetic fields, finally snaps in a starquake. But what twists the fields in the first place? One theory points to the core's superfluidity. If neutrons in the inner crust flow without friction, they could drag magnetic field lines along with them, tangling them into unstable configurations. When these tangled lines suddenly reorganize, the energy release could be catastrophic, like a rubber band stretched to its limit and then let go. But there's another, even wilder possibility. If the core contains strange matter or free quarks, their movements might generate magnetic fields through entirely different mechanisms. Quarks, unlike neutrons, carry electric charge, and in a dense quark-gluon plasma, their collective behavior could create currents far more intense than anything possible in ordinary matter. Some models even suggest that quark vortices spinning whirlpools of quark matter could act like microscopic cosmic dynamos, amplifying magnetic fields to magnetar levels. The stakes of this puzzle couldn't be higher. Magnetars aren't just curiosities, they're natural laboratories for physics we can't replicate on Earth. By studying their outbursts, their spin-down rates, and even the subtle wobbles in their rotation, we might finally glimpse the core's secrets. Every flicker of X-rays, every ripple in space-time, carries hints about what's happening in that hidden realm. And if we crack this code, we won't just understand magnetars, we'll unlock new chapters in the story of matter itself. Neutron stars don't just fade quietly into the cosmic background. They blaze their final chapters in a shower of ghostly particles called neutrinos, tiny messengers that could hold the key to unlocking their deepest secrets. These stars, born in the fiery chaos of supernova, start their lives scorching hot, with temperatures reaching trillions of degrees. But without an external heat source, they can't stay that way forever. The chilling process isn't just a slow cool down. It's a dramatic exodus of energy, with neutrinos carrying away heat so efficiently that they can outshine the star's visible light by a factor of billions. And here's the catch: how fast this happens depends entirely on what's happening in the core. Imagine two neutron stars, identical in size and age, but one cools twice as fast as the other. Why? The answer might lie in exotic particles like hyperons or free quarks swirling in their cores. These particles don't just sit idly, they interact with the surrounding matter in ways that turbocharge neutrino production. Hyperons, for instance, can decay into lighter particles, releasing a flurry of neutrinos in the process. Quark matter, if it exists, might enable reactions so efficient they act like a cosmic radiator, bleeding heat into space at an astonishing rate. On the other hand, a core made purely of neutrons would cool more sluggishly, like an ember taking centuries to fade. The smoking gun for these theories could come from telescopes like NASA's Chandra X-ray Observatory or the upcoming Athena mission. By measuring the surface temperatures of neutron stars at different ages, astronomers can piece together cooling curves graphs that show how quickly these objects lose heat. Some stars, like Cassiopeia A's neutron star, have puzzled scientists by cooling far faster than standard models predict. The leading explanation: a phase transition in its core where neutrons dissolve into quark matter, unleashing a cascade of neutrinos that accelerate the star's cooling like a sudden draft through an open window. But neutrino cooling isn't just a one-way street. In some scenarios, exotic core materials might actually slow the process down. If protons in the core form a superconductor, their paired-up electrons could block certain neutrino-producing reactions, effectively putting a lid on the cooling rate. It's like wrapping the star in an insulating blanket, trapping heat that would otherwise escape. This could explain why some middle-aged neutron stars seem warmer than they should be. Their cores might be cloaked in a quantum state we've yet to fully understand. The stakes of this detective work couldn't be higher. Every neutrino that flees a neutron star carries information about the extreme physics happening in its heart. Future detectors like the Hypercamioc, an experiment in Japan, could catch these elusive particles in the act, offering a direct window into processes we can't observe any other way. Combine that with gravitational wave data from colliding neutron stars, and we might finally crack the code of what's hidden beneath those impenetrable surfaces. The universe is whispering its secrets in a language of particles and heat. All we have to do is listen. When two neutron stars spiral toward each other in a cosmic dance, they don't just crash, they shake the very fabric of the universe. The gravitational waves unleashed in these collisions ripple outward at the speed of light, carrying encoded details about the star's most hidden depths. Unlike light or X-rays, which only skim the surface, these space-time distortions offer something revolutionary: a direct line of sight into the heart of neutron stars, where matter exists in states beyond our wildest imagination. The breakthrough came in 2017, when detectors LIGO and Virgo captured the first gravitational waves from a neutron star merger, an event dubbed GW 170,817. The signal wasn't just a fleeting chirp, it was a treasure trove of data. As the stars orbited each other hundreds of times per second before colliding, their gravitational waves subtly shifted in tone, like a cosmic flute playing a descending scale. These changes revealed how the stars deformed under each other's gravity, a clue to their internal stiffness. If the cores were pure neutrons, they'd resist distortion like a rigid sphere. But if quark matter or hyperons lurked inside, the stars might squish more easily, altering the gravitational wave signature in telltale ways. What makes these observations so groundbreaking is their precision. By combining gravitational wave data with bursts of gamma rays and light from the same event, a first in astronomy, scientists could cross-check their models against reality. The results hinted at something astonishing. The merged object might have briefly formed a hypermassive neutron star with a quark core before collapsing into a black hole. That fleeting moment, lasting mere milliseconds, could be our best evidence yet of exotic matter hiding in plain sight. Future collisions promise even sharper insights. Upgraded detectors like LIGO Voyager or the Einstein telescope will catch finer details in the waves, potentially spotting phase transitions in real time, like the moment a neutron star's core flips from neutrons to quark matter mid-collision. Some theories predict these transitions would produce distinctive kinks in the gravitational wave signal, sudden changes in frequency as the star's internal structure reorganizes. Others suggest the waves might carry echoes, faint repetitions caused by quark matter's unusual properties, reflecting space-time ripples in unexpected ways. But gravitational waves aren't just passive messengers. The act of collision itself could forge entirely new states of matter. When neutron stars merge, temperatures briefly soar to trillions of degrees, recreating conditions not seen since the universe's first second. In this primordial furnace, quarks might break free not just in droplets, but in vast oceans, their behavior imprinting onto the gravitational waves like a fingerprint. If strange matter forms, even fleetingly, its unique signature could linger in the data, a smoking gun for one of astrophysics' most elusive hypotheses. The challenge now is decoding these cosmic ciphers. Each gravitational wave signal is a puzzle wrapped in layers of noise, requiring supercomputers and cutting-edge algorithms to unravel. Yet with every new collision detected, the picture grows clearer. We're not just listening to the universe's symphonies, we're learning to understand the instruments themselves, one cataclysmic crash at a time. Pulsars are the universe's most precise timekeepers, spinning neutron stars that beam radiation like cosmic lighthouses with such regularity. They rival atomic clocks. But every now and then, these celestial metronomes stutter. A pulsar's rotation might suddenly speed up by a fraction of a second, a phenomenon called a glitch, as if the universe itself hit the fast-forward button. These tiny hiccups aren't just random quirks, they're cosmic telegrams carrying encrypted details about the chaotic, hyper-dense realms buried deep inside the star. The secret to decoding these glitches lies in the neutron star's layered structure. Picture the star's crust, a rigid lattice of atomic nuclei, floating atop a swirling ocean of superfluid neutrons particles moving without friction like a ghostly liquid. Normally, the crust and superfluid rotate in sync, but as the star's magnetic field and radiation gradually slow the crust down, the superfluid resists, lagging behind like a flywheel storing energy. When the tension between these layers becomes too great, the superfluid's vortices, tiny whirlpools of spinning neutrons, suddenly reorganize, transferring a burst of angular momentum to the crust. The result, a glitch. It's like a figure skater pulling their arms in mid-spin, but scaled up to cosmic forces. But glitches might reveal more than just neutron dynamics. Some pulsars exhibit macroglitches, disruptions so large they defy conventional explanations. These could be smoking guns for exotic core materials, like quark matter or hyperons altering the star's internal friction. If part of the core transitions into a quark-gluon plasma, for instance, its sudden stiffness or slippage might send shockwaves through the star, triggering a glitch far more dramatic than superfluid vortices alone could produce. The Vela pulsar, one of the most glitch-prone neutron stars known, offers a tantalizing case study. Its frequent, unpredictable jumps in spin rate suggest something turbulent is happening beneath the surface, possibly tied to phase transitions in its core. Pulsar timing isn't just about watching for glitches, it's about listening to the star's entire vibrational language. Tiny changes in pulse arrival times, down to nanosecond precision, can hint at starquakes, shifts in magnetic field geometry, or even gravitational waves passing through the star. The longer we observe a pulsar, the more its subtle rhythms paint a portrait of its hidden depths. Millisecond pulsars, which spin hundreds of times per second, are particularly revealing. Their extreme stability makes any deviation, a missed tick in their rhythm, stand out like a wrong note in a symphony, pointing directly to internal upheavals. What makes this detective work so revolutionary is its reach. Unlike gravitational waves or neutrino emissions, which require cataclysmic events like collisions, pulsar glitches happen quietly, constantly, in neutron stars across the galaxy. Each anomaly is a breadcrumb leading us closer to answering the big questions. Does quark matter exist in their cores? Are hyperons dancing in the depths? With every flicker of a pulsar's beam, we're not just keeping time, we're unraveling the universe's most extreme physics, one rotation at a time. The equation of state isn't just a dry scientific term, it's the master key that unlocks the secrets of a neutron star's core. Think of it like a cosmic recipe dictating how matter behaves under unimaginable pressures. At everyday densities like those on Earth, matter follows predictable rules. Squeeze it and it resists. But inside a neutron star, where gravity crushes material to 1 trillion times the density of steel, the equation of state becomes a battleground of quantum forces, determining whether the core remains a sea of neutrons or fractures into something far stranger. One leading theory suggests the core is a neutron-dominated landscape, with particles packed so tightly they form a superfluid, a frictionless quantum liquid capable of swirling endlessly without losing energy. But another camp argues that under such extremes, neutrons themselves break apart, their quarks spilling out to create a soup of free floating particles. Then there's the strange matter hypothesis, where quarks reorganize into an ultra-stable configuration that could rewrite the rules of physics. Each possibility hinges on the equation of state, a mathematical relationship between pressure and density that's anything but simple. The stakes couldn't be higher. If the equation favors stiff matter resistant to compression, neutron stars could grow more massive without collapsing, explaining why some defy theoretical size limits. But if matter is softer, with particles that yield easily to pressure, stars might transition into quark matter cores far sooner than we've observed. The challenge: we can't recreate these conditions in any lab on Earth. Instead, scientists rely on cosmic clues, the gravitational waves from colliding neutron stars, the precise timing of pulsar rotations, even the way these stars cool over millennia. Each data point narrows down the possibilities, like piecing together a puzzle where the final image could shatter our understanding of reality. What makes this search so thrilling is how personal it feels. Every tweak to the equation of state isn't just an academic exercise. It's a step closer to answering questions that have haunted physicists for decades. Are we alone in the universe? What happened in the first moments after the Big Bang? The heart of a neutron star might hold the answers, encrypted in the language of pressure, density, and quantum uncertainty. And with every new observation, we're one step closer to cracking the code. Dark matter could be hiding in the last place we'd think to look: the heart of a neutron star. While these cosmic behemoths are already packed with bizarre forms of ordinary matter, some scientists speculate they might also act as dark matter traps, capturing particles that barely interact with anything else in the universe. If true, this could rewrite not just our understanding of neutron stars, but the very nature of dark matter itself. Here's how it might work. Dark matter, which makes up roughly 27% of the universe's mass, is thought to drift through space mostly unnoticed, barely touching ordinary matter. But inside a neutron star, gravity's pull is so intense that even these elusive particles could get snagged. over billions of years, dark matter might accumulate in the core, subtly altering the star's density, heat distribution, or even its stability. Some models suggest that enough dark matter could counteract the crushing force of gravity, preventing the star from collapsing into a black hole even at higher masses. Others propose that interactions between dark matter and the star's ultra-dense material could generate heat, slowing the cooling process in ways we might detect from Earth. The implications are staggering. If neutron stars do harbor dark matter, they could become natural detectors for this mysterious substance, ones far more sensitive than any Earth-based experiment. Unlike underground labs that wait for the rare collision between dark matter and atomic nuclei, a neutron star's extreme gravity could pull in dark matter continuously, amplifying its effects over time. A slight change in a star's cooling rate, an unexpected glitch in its rotation, or even an anomalous gravitational wave signal during a collision might betray the presence of these hidden particles. But there's a catch. Dark matter's behavior depends entirely on properties we don't yet understand. If it's made of weakly interacting massive particles WIMP, their collisions with neutrons could generate detectable energy. If it's something stranger like actions or primordial black holes, the effects might be subtler, hidden in the star's magnetic fields or vibration patterns. And if dark matter doesn't interact at all beyond gravity, its presence might be nearly impossible to spot. The search is already underway. Astronomers are scouring pulsar timing data for anomalies that could hint at dark matter's influence. Others are simulating how different dark matter candidates would behave inside neutron stars, predicting observable signatures. It's a long shot, but if we find even a whisper of evidence, it could solve two cosmic mysteries at once: what neutron stars are truly made of, and what dark matter actually is. The universe loves hiding its secrets in plain sight. This time, they might be buried in the densest objects it's ever created. Neutron stars aren't just cosmic oddities, they're laboratories for physics so extreme, they push the boundaries of what we thought was possible. The Standard Model, our best blueprint for how particles and forces interact, works flawlessly here on Earth, but inside a neutron star, where densities and pressures defy imagination, cracks in that model might finally show themselves. This is where the universe could be hiding answers to questions we haven't even thought to ask yet. Take the mystery of dark photons, hypothetical particles that could bridge the gap between ordinary matter and dark matter. In the crushing depths of a neutron star's core, where electromagnetic forces are dwarfed by nuclear interactions, dark photons might emerge from the chaos, subtly altering how energy escapes the star. Or consider actions, another theoretical particle born from attempts to solve quantum puzzles. If they exist, neutron stars' intense magnetic fields could convert actions into detectable X-rays, offering us a backdoor to observing these elusive entities for the first time. But it's not just about particles. The strong nuclear force which holds atomic nuclei together behaves differently under neutron star conditions. At these densities, the space between protons and neutrons vanishes, and the force's normal rules might break down entirely. Some theories suggest that quarks, normally confined inside particles, could form unbroken chains stretching across the core, a state of matter that would rewrite our understanding of quantum confinement. Others speculate that gravity itself might behave differently at these scales, subtly bending Einstein's rules in ways only detectable in such an extreme environment. The beauty of these cosmic experiments is their inevitability. Unlike Earth-based colliders, which require monumental energy to recreate fleeting high-energy conditions, neutron stars do the work for us, sustaining pressures and densities we could never achieve in a lab. When two neutron stars collide, the resulting fireball reaches temperatures 1,000,000 times hotter than the Sun's core, potentially birthing particles or phases of matter that haven't existed since the Big Bang. Gravitational waves from these crashes carry fingerprints of the star's internal structure, hinting at whether exotic physics played a role in their final moments. What's at stake isn't just academic. Discovering new physics in neutron stars could answer why our universe is made of matter instead of antimatter, or whether dark matter interacts with ordinary matter in ways we've missed. Every glitch in a pulsar spin, every anomalous cooling rate, every gravitational wave signal might be a clue waiting to be deciphered. The universe has built the ultimate particle accelerator, and it's been hiding in plain sight, spinning silently in the void. If strange matter truly exists in the cores of neutron stars, there's a spine-tingling possibility tiny fragments of it could break free and roam the cosmos. These hypothetical pieces, dubbed Strangelets, would be unlike anything else in the universe, droplets of ultra-dense quark matter, potentially more stable than the atoms that make up our world. The idea isn't just science fiction. When neutron stars collide or undergo violent starquakes, the unimaginable energies involved could eject shreds of their cores into space, sending strangelets racing across the galaxy at near light speed. And here's the unsettling part: some might be headed straight for Earth. Cosmic rays, those high-energy particles that constantly bombard our atmosphere, are mostly protons or atomic nuclei. But buried in that rain of ordinary matter, there could be rare, exotic outliers, strangelets that survived their journey across interstellar space. Theoretically, these particles would pack insane density. A speck the size of a virus could weigh as much as a battleship, its quarks locked in that perfect, stable configuration strange matter promises. Detecting them, though, is like finding a needle in a cosmic haystack. Most would zip through Earth unnoticed, their interaction so feeble they'd leave no trace. But if one struck an atomic nucleus in just the right way, it might trigger a cascade of unusual particle decays, or even, in the most dramatic scenarios, convert nearby matter into strange matter itself. The hunt for these phantom particles has turned up empty so far. Experiments like the Alpha Magnetic Spectrometer aboard the International Space Station have sifted through countless cosmic rays, searching for anomalies that could betray a strangelet's passage. Other detectors, like those buried deep underground, listen for the faint tremors of a strangelet colliding with Earth's atoms, yet no confirmed sightings exist. Critics argue this silence is telling. If strangelets were real and stable, shouldn't the universe be littered with them? Supporters counter that they might simply be too rare or too subtle to spot with current technology. The implications of finding one, though, would be staggering. A single confirmed strangelet could prove that quark matter isn't just a theoretical curiosity. It's a tangible reality, lurking in neutron star cores and occasionally escaping into the wild. It might also solve lingering mysteries about cosmic rays. Some ultra-high-energy particles detected on Earth seem to defy explanation, with energies far beyond what supernova or black holes should produce. Could strangelets forged in the heart of neutron star collisions be the culprits? For now, the search continues, a high-stakes game of cosmic hide and seek. Every unexplained blip in a detector, every anomalous cosmic ray, could be the clue that cracks the case. And if strangelets are out there, they're not just remnants of distant stars. They're messengers carrying secrets from the universe's most extreme laboratories straight to our doorstep. Simulating the heart of a neutron star is like trying to map a hurricane with a pocket calculator. The forces at play are so extreme, so chaotic, that even our most powerful supercomputers buckle under the weight of the calculations. Picture this: a single cubic centimeter of neutron star core contains around 400 million tons of matter, with particles moving at near light speeds under pressures that crush atomic structures into oblivion. To recreate these conditions digitally, scientists must solve equations describing quantum interactions between trillions upon trillions of particles, each influencing the others in ways that ripple across the entire system. It's not just a computational challenge, it's a frontier where raw processing power meets the limits of human imagination. Current simulations often rely on simplifying assumptions, like treating chunks of the core as uniform fluids or ignoring certain particle interactions to make the math manageable. But these shortcuts come at a cost. They might miss subtle phase transitions the moment neutrons dissolve into quarks, for instance, or fail to capture how exotic particles like Hyperons alter the core's stiffness. That's where next-generation simulations are breaking ground. Projects like the Einstein Toolkit and SPEC use adaptive mesh refinement, a technique that zooms in on critical regions while keeping the broader structure intact. Think of it like a cosmic microscope. Instead of blurring the entire star into pixels, it focuses computational resources where the action is hottest, whether that's a quark matter bubble forming or a magnetic field knotting itself into instability. The real game changer, though, is machine learning. By training neural networks on known physics principles, researchers can let algorithms guess the behavior of matter in uncharted regimes, filling gaps where equations fall short. In 2022, a team at the University of Illinois fed their model data from particle colliders and gravitational wave observations, then set it loose on a simulated neutron star merger. The result, a prediction that quark matter might form fractal-like patterns in the collision's aftermath, structures no human physicist had thought to look for. It's a glimpse of how artificial intelligence isn't just crunching numbers, it's helping us ask better questions, yet even these advances have hard limits. Some quantum effects, like the entanglement of particles across the entire core, require computations so vast they demand a supercomputer the size of a planet. Others, like the exact role of dark matter in neutron stars, remain pure speculation until observational data catches up. That's why the latest simulations aren't standalone answers, they're dialogues. Each result is compared against pulsar glitches, gravitational wave signals, and even lab experiments with ultra-cold atoms that mimic neutron star superfluidity. When a simulation contradicts reality, it's not a failure, it's a signpost pointing toward physics we've yet to grasp. What makes this effort so extraordinary isn't just the technology, it's the stakes. Every line of code, every refined algorithm, brings us closer to answering whether quark matter exists, if strange matter is stable, or how hyperons dance in the dark. These aren't abstract puzzles, they're keys to understanding the universe's most violent explosions, the birth of black holes, even the origins of elements like gold and platinum. The core of a neutron star isn't just a scientific curiosity, it's a Rosetta Stone for decoding the cosmos, and simulations are our first shaky steps toward fluency. The next generation of space telescopes is gearing up to peel back the layers of neutron stars like never before. Imagine instruments so precise they could detect temperature variations smaller than a degree across surfaces thousands of light-years away. Missions like Europe's Athena X-ray Observatory and NASA's Lynx are designed to do exactly that. These aren't just incremental upgrades, they're quantum leaps in our ability to probe the universe's most extreme environments. Athena, slated for launch in the 2030s, will carry an X-ray spectrometer with 100 times the sensitivity of current tools, capable of mapping the thermal fingerprints of neutron star crusts in exquisite detail. Every flicker of X-rays, every subtle shift in emission patterns could betray the turmoil happening deep below the surface, where exotic matter might be churning unseen. But Athena's real power lies in timing. By monitoring neutron stars over years, even decades, it could catch the moment a starquake realigns the crust or a phase transition in the core subtly alters how heat escapes. Picture it like a cosmic stethoscope, listening for the heartbeat of a star's internal dynamics. Meanwhile, a Lynx mission takes this even further. With resolution sharp enough to distinguish features just a few kilometers across on a neutron star's surface, Lynx could spot hotspots where magnetic fields punch through the crust, or regions where cooling rates deviate unexpectedly, hinting at uneven quark matter formation beneath. Combined, these telescopes won't just observe neutron stars, they'll dissect them layer by layer. The stakes are higher than mere curiosity. When neutron stars collide, they forge elements like gold and platinum in their wake, but the exact recipe depends on what's happening in their cores. Athena and Lynx could catch the aftermath of these collisions, analyzing the X-ray afterglow for clues about whether quark matter or hyperons played a role in the explosion. Even more tantalizing, if strange matter exists, these observatories might spot its signature in the way certain neutron stars cool or how their magnetic fields evolve over time. A single anomalous dataset could upend decades of theory, yet the most revolutionary insights might come from the unexpected. In science, it's often the surprises, the data points that don't fit the models, that lead to breakthroughs. What if these telescopes reveal neutron stars cooling too fast or too slow, defying all predictions? What if they catch a Magnetars outburst in unprecedented detail, exposing processes we've never even imagined? The universe has a habit of being stranger than fiction, and with tools this powerful, we're not just looking for answers, we're ready to be astonished. The cores of neutron stars have kept their secrets for billions of years. Their time is almost up. String theory might seem like the most abstract corner of physics, a realm of extra dimensions and vibrating strings far removed from the tangible cosmos. But hidden in its equations lies a radical idea that could crack open the neutron star mystery: holographic duality. Picture this concept as a cosmic mirage, where the messy, three-dimensional chaos inside a neutron star's core might be perfectly mirrored by a tidier, two-dimensional description on its surface. It sounds like science fiction, but this principle, born from black hole physics, is now offering astronomers a backdoor into understanding matter at its most extreme. At its heart, holographic duality suggests that the information about what's happening deep inside a neutron star, the quark collisions, the hyperon dances, the possible strange matter, could be encoded in the vibrations and fluctuations on its surface. Think of it like a DVD. The movie's vivid, three-dimensional action is stored as microscopic pits on a flat, two-dimensional disk. In the same way, a neutron star's surface ripples, captured by next-gen telescopes, might reveal the quantum storms raging in its core. Already, theorists are using this approach to model how quark-gluon plasma might behave under neutron star pressures, sidestepping the near-impossible calculations required by conventional methods. But the implications go even deeper. If holographic duality holds, it could redefine how we study all dense astrophysical objects. Gravitational waves from colliding neutron stars, for instance, might carry holographic echoes, subtle distortions in spacetime that betray the core's true composition. Some models even suggest that the star's magnetic field, which twists and knots in ways we still don't fully understand, could be a surface projection of far stranger dynamics below. It's as if the universe handed us a decoder ring, and we're just starting to recognize the cipher. Yet for all its promise, holographic duality isn't a magic bullet. Critics argue that simplifying neutron stars to 2 dimensions might gloss over critical 3-dimensional effects, like how quark matter crystallizes or how hyperons interact at different depths. Others point out that the mathematics remains so complex, it's like trading one unsolvable puzzle for another. Still, the mere possibility has ignited collaborations between string theorists and astrophysicists that were unthinkable a decade ago. Together, they're asking, if a neutron star's surface really is a hologram of its core, what secrets is it scrambling to hide? The answer might lie in the data. Upcoming missions like the Square Kilometer Array with its army of radio telescopes could detect pulsar surface vibrations precise enough to test holographic predictions. Meanwhile, labs like CERN are recreating microsecond glimpses of quark gluon plasma, offering ground truth comparisons. Whether holographic duality survives these tests or not, it's already done something remarkable. Turned neutron stars from cosmic curiosities into proving grounds for the most cutting-edge ideas in physics. The universe's densest objects might just be the key to unifying its deepest theories. Deep within the violent chaos of colliding neutron stars, the universe operates its most spectacular alchemy, transforming the simplest particles into gold, platinum, and other precious metals. For decades, scientists puzzled over the origins of these heavy elements. Supernovae were once thought to be the primary cosmic forges, but their models couldn't account for the sheer abundance of gold in the universe. Then came the game-changing discovery in 2017, when the collision of 2 neutron stars event GW 170,817 was observed for the first time. The aftermath wasn't just a burst of gravitational waves, it was a fireworks display of light across the spectrum, rich with signatures of freshly synthesized heavy elements. Telescopes detected telltale streaks of infrared glow, the fingerprint of newly forged gold and platinum thrown into space at staggering speeds. The process behind this cosmic minting is as extreme as it gets. When neutron stars spiral into each other, their merger creates conditions hotter than the sun's core and denser than an atomic nucleus. In this maelstrom, neutrons are ripped free in unimaginable quantities, flooding the surrounding debris with a neutron-rich soup. Atoms caught in this torrent undergo rapid neutron capture, or the R process, a chain reaction where atomic nuclei gorge on neutrons faster than they can decay, ballooning into heavier and heavier elements. Within seconds, this frenzy can produce gold hundreds of times Earth's mass, along with platinum, uranium, and other rarities. It's like stuffing a pinata with matter until it bursts, scattering precious metals across the cosmos. But the real intrigue lies in what happens before the collision. Neutron star cores, already packed with degenerate matter, might be pre-processing these elements in their deepest layers. Some theories suggest that during a star's life, slow neutron capture, the S process could seed its crust with heavy elements which then get ejected during mergers. Others propose that quark matter in the core, if it exists, might catalyze unusual nuclear reactions, churning out exotic isotopes that later decay into gold. The challenge is that these cores are so opaque to observation that we're left piecing together clues from the debris they leave behind. What makes this puzzle so urgent isn't just academic. Every gold ring or platinum necklace on Earth might trace its lineage to these cataclysmic crashes. The very atoms in our jewelry could have been born in a neutron star collision billions of years ago, flung across space before condensing into the solar system. Future telescopes like the James Webb Space Telescope's successors aim to spot more of these mergers, analyzing their light for elemental fingerprints. With each new detection, we're not just solving a cosmic mystery, we're rewriting the story of our own origins, one glittering fragment at a time. Among the strangest cosmic survivors are the planets orbiting Pulsar's neutron stars that should have annihilated everything in their vicinity during their violent birth. Take PSRB 1257+12, a pulsar with at least 3 planets, including one barely twice the mass of our moon. These worlds defy logic. They circle the remnants of a supernova explosion so powerful it should have vaporized any nearby material. Yet there they are, clinging to existence in the gravitational grasp of a stellar corpse spinning hundreds of times per second, blasting its surroundings with lethal radiation. How did they endure? The answer might lie in the neutron star's hidden core, whose exotic physics could shape these planetary systems in ways we're only beginning to understand. One theory suggests these planets aren't survivors at all, they're cosmic phoenixes, born from the ashes of the explosion. When a massive star goes supernova, its outer layers are hurled into space, but some debris might fall back, forming a disk around the newborn neutron star. Over time, this material could clump together, forging new worlds from the shattered remains of the old. Here's where the core's composition becomes critical. If the neutron star contains quark matter or hyperons, its intense gravity and magnetic fields might churn the debris disk differently, altering how planets coalesce. A stiffer core, for instance, could produce stronger gravitational ripples, herding dust and gas into tighter orbits where terrestrial planets form. Alternatively, a superfluid core might dampen these vibrations, allowing gas giants to take shape farther out. But the real wildcard is radiation. Pulsars don't just spin, they fire off beams of X-rays and gamma rays like cosmic lighthouses, sterilizing anything in their path. Yet some of these planets orbit breathtakingly close, bathing in that lethal energy. Their survival hints at another layer of strangeness, the neutron star's magnetic field, which could be shaped by core dynamics. If protons in the core form a superconductor, their paired movements might generate a magnetic shield around the planets, deflecting the worst of the radiation. Or perhaps the planets themselves are unlike anything in our solar system, ultra-dense remnants of white dwarfs, stripped to their metallic cores by the pulsar's fury, their iron-rich bodies resistant to evaporation. The most tantalizing possibility, these systems might harbor life, not as we know it but as we can't imagine. On a pulsar planet, the energy isn't sunlight but the relentless glow of X-rays. The heat isn't geothermal but frictional, generated by tidal forces flexing the world's crust. Any life here would exist in a reality where chemistry follows different rules, where magnetic fields replace atmospheres, and where the very ground beneath your feet hums with the vibration of a spinning neutron star. It's a reminder that the universe's creativity doesn't end with Earth-like worlds sometimes. It begins where we'd least expect. Studying these systems isn't just about cataloging oddities. Each pulsar planet is a stress test for our theories of planet formation, stellar evolution, and the extreme physics of neutron star cores. When the James Webb Space Telescope turns its eye toward these enigmas, analyzing the faint infrared glow of their irradiated surfaces, we might find clues etched in their spectral lines, hints about the core's composition, the supernova's aftermath, or even entirely new classes of celestial bodies. The universe has a habit of hiding its most profound lessons in the unlikeliest places. This time, they're orbiting the universe's deadliest stars. Neutron stars aren't just cosmic oddities, they're frozen relics of the universe's most violent moments, preserving conditions so extreme they haven't existed since the Big Bang's first seconds. Locked within their cores are echoes of a time when quarks roamed free, and the four fundamental forces were indistinguishable from one another. Think of them as celestial time capsules, sealed under pressures 100 trillion times greater than Earth's atmosphere, where matter is compressed to densities that turn the familiar laws of physics into a quantum free-for-all. What makes these stellar fossils so invaluable is their ability to simulate environments no lab on Earth could ever recreate. The early universe was a seething cauldron of quark gluon plasma, a state where particles moved freely without forming protons or neutrons. While particle colliders like the Large Hadron Collider can produce microscopic droplets of this primordial soup for fractions of a second, neutron stars sustain these conditions continuously across volumes larger than cities. Their cores might be the only places in the modern universe where quark matter exists in bulk, letting us study how it behaves over astronomical timescales rather than fleeting moments. But the revelations don't stop there. Neutron stars could hold answers to one of physics' biggest mysteries: how the strong nuclear force, which binds quarks into protons and neutrons, operates under conditions so extreme it begins to break its own rules. Normally, this force grows stronger with distance, a property called confinement that keeps quarks forever locked inside particles. Yet in a neutron star's core, where particles are crammed shoulder to shoulder, the rules might flip. Quarks could become asymptotically free, ignoring one another entirely, or form entirely new types of bonds that don't exist anywhere else in nature. The most tantalizing possibility: these stars might be hiding evidence of unified forces. In the universe's first moments, electromagnetism and the weak nuclear force were one and the same, a merger that only broke apart as the cosmos cooled. Neutron star cores, with their mind-bending densities, could be forcing these forces back together, creating hybrid phenomena we've never observed. Some theories even suggest their magnetic fields, amplified to impossible strengths, might reveal how gravity fits into the quantum puzzle, a stepping stone toward the long-sought theory of everything. Every glitch in a pulsar spin, every anomalous gravitational wave from a neutron star collision, is a whisper from the early universe, begging us to listen closer. By decoding these messages, we're not just studying distant objects, we're peering back in time, uncovering secrets that have been locked away since the dawn of existence itself. The universe's infancy is written in the heart of these stellar relics, waiting for us to translate its wild, untamed physics. If neutron star cores harbor forms of matter unlike anything we've ever encountered, the implications ripple far beyond astrophysics. They force us to confront fundamental questions about the nature of reality itself. Consider this: what we call normal matter, the atoms, molecules, and forces that shape our everyday world, might be just a tiny fraction of existence's full spectrum. The universe could be teeming with states of matter so alien that they operate by entirely different rules, hidden away in these cosmic pressure cookers. This isn't just about adding new entries to the periodic table. It's about rewriting the very definition of what matter is. Philosophers have long grappled with the idea that reality might be far stranger than our senses perceive. Neutron stars offer a tangible glimpse into that strangeness. If quark matter or strange matter exists in their cores, stable and self-sustaining, it challenges the Aristotelian notion that matter has a fixed, immutable essence. Instead, we're left with a universe where solidity and stability are relative, where the bedrock of physical existence shifts under extreme conditions. Even the concept of emptiness dissolves. A neutron star's core is so dense that the space between particles vanishes, rendering the very idea of void meaningless. Then there's the metaphysical puzzle of identity. If a neutron star's core transitions into quark matter, does it remain the same object, or does it become something fundamentally new? Ancient philosophers debated whether a ship, after having every plank replaced, was still the original ship. Neutron stars pose a quantum-age version of that paradox. At what point does matter, reconfigured beyond recognition, cease to be itself? These aren't abstract thought experiments. The answers could redefine how we classify everything from subatomic particles to the fate of the cosmos. Ethically, the stakes are just as profound. If strange matter is stable and contagious, could it theoretically transform ordinary matter upon contact? While the odds of such a scenario are vanishingly small, the mere possibility forces us to weigh the risks of probing too deeply into nature's secrets. Humanity's curiosity has unlocked countless wonders, but neutron stars remind us that some knowledge might come with existential stakes. Should we deliberately recreate quark gluon plasma in colliders, knowing it mimics conditions that could, in theory, unravel the fabric of reality? The line between discovery and hubris has never been thinner. Ultimately, neutron stars serve as cosmic mirrors, reflecting our deepest questions back at us. They blur the boundaries between physics and philosophy, between the observable and the unimaginable. Every new revelation about their cores doesn't just expand our scientific horizons, it reshapes what it means to know something, to exist within a universe that remains, in so many ways, beautifully and terrifyingly opaque. Neutron stars are often misunderstood, oversimplified into familiar concepts that don't capture their true strangeness. One common myth paints them as nothing more than gigantic atomic nuclei, a sea of neutrons packed together like marbles in a jar. While it's true their cores are dominated by neutrons, this comparison falls apart under scrutiny. An atomic nucleus is held together by the strong nuclear force, but a neutron star's stability is a cosmic tug of war between that same force and gravity's relentless crush. The pressures inside are so extreme that even the rules governing nuclear physics bend and warp, creating states of matter that don't exist anywhere else in the universe. Calling a neutron star just a big atom is like calling a hurricane a big breeze. It misses the sheer scale of complexity at work. Another persistent misconception is that neutron stars are essentially black holes in disguise, objects so dense they're on the verge of collapsing into singularity. While both are born from stellar death, the differences are profound. A black hole's gravity is so intense that nothing, not even light, can escape its event horizon. Neutron stars, though unimaginably dense, still have surfaces and structures we can observe indirectly. Their magnetic fields, pulsar emissions, and even starquakes leave detectable fingerprints. Think of it this way: if a black hole is a cosmic vacuum cleaner, sucking everything into oblivion, a neutron star is more like a diamond under a hydraulic press, pressed to its limits, but still intact, still shining in its own way. Then there's the idea that neutron stars are indestructible, immutable objects. In reality, they're dynamic and volatile. Take Magnetars, neutron stars with magnetic fields so powerful they could strip data from a credit card halfway across the galaxy. These fields aren't static. They twist, snap, and reconnect, unleashing bursts of energy that can briefly outshine entire galaxies. Even the star's crust, often imagined as unbreakable, can fracture under stress, triggering starquakes that ripple through the star's interior. These aren't the behaviors of some inert cosmic relic, they're signs of a living, evolving system, seething with activity beneath its seemingly placid surface. Perhaps the most tantalizing myth is that we've got neutron stars all figured out. The truth, every new observation throws a wrench into our models. Some neutron stars spin faster than our theories say they should. Others cool down too quickly or refuse to collapse into black holes at predicted masses. These anomalies aren't failures of science, they're breadcrumbs leading us toward deeper truths. When a pulsar's timing glitches or a gravitational wave signal doesn't match expectations, it's not a dead end. It's the universe nudging us to look closer, to question assumptions, and to embrace the fact that the most exotic objects in the cosmos still have secrets to spill. The beauty of these cosmic enigmas isn't just in debunking myths, it's in revealing how much wilder reality is than our simplifications. Neutron stars aren't just bigger, denser versions of things we know. They're laboratories for physics we can't replicate, windows into the universe's most extreme conditions, and reminders that nature's creativity dwarfs our imagination. What we've learned so far is thrilling. What we haven't learned, that's where the real adventure begins. Imagine having a supercomputer at your fingertips, crunching cosmic data while you sleep. That's the power of projects like Einstein at home, where ordinary people become citizen scientists, sifting through the universe's secrets from their living rooms. This isn't just busy work. Volunteers have already made groundbreaking discoveries, like identifying previously unknown pulsars hidden in mountains of telescope data. Your laptop could be the next tool to spot a neutron star's faint whisper in the noise of the cosmos, revealing clues about what's happening deep inside those ultra-dense cores. The beauty of these initiatives lies in their simplicity. Einstein at home taps into idle processing power from thousands of devices worldwide, creating a distributed supercomputer capable of analyzing gravitational wave signals, pulsar rotations, and even gamma-ray bursts. Every click of participation helps scientists test theories about quark matter or hyperons by comparing real-world data against simulations. In 2016, a German schoolteacher and an American systems analyst, both volunteers, co-discovered a rare neutron star orbiting another massive star, proof that you don't need a PhD to advance astrophysics. But the contributions go beyond number crunching. Platforms like Zooniverse let enthusiasts visually inspect neutron star light curves or classify magnetar flares, tasks where human intuition still outpaces algorithms. When the Neutron Star Interior Composition Explorer, or NICER, beams data from the International Space Station, citizen scientists help flag anomalies that might indicate starquakes or magnetic field shifts, events that could hint at phase transitions in the core. It's like a global treasure hunt where anyone might stumble on a clue that rewrites textbooks. The ripple effects are profound. By democratizing research, these projects don't just accelerate discoveries, they foster a deeper public connection to the cosmos. A teenager in Mumbai might notice a pulsar's timing glitch that hints at strange matter, while a retiree in Oslo could help model how gravitational waves from colliding neutron stars distort under exotic core physics. Together, they're part of a collective effort to answer some of science's biggest questions, proving that unraveling the universe's mysteries isn't just for elite institutions. It's a shared human adventure powered by curiosity and a screensaver. Neutron stars have long captured the imagination of storytellers, appearing in everything from blockbuster films to epic video games as the ultimate cosmic spectacles. Take the iconic scene from Interstellar, where the crew navigates near a supermassive black hole. While not a neutron star, the film's portrayal of extreme gravity and time dilation borrows heavily from real neutron star physics. The visuals of light bending around the void, that's rooted in actual science, but Hollywood often cranks the drama to 11. For instance, many movies depict neutron stars as volatile, explosive objects, when in reality, their danger lies in their crushing gravity and radiation, not Hollywood-style detonations. Video games, too, love neutron stars as high-stakes playgrounds. Elite Dangerous lets players pilot ships through their intense magnetic fields, where navigation errors mean instant obliteration. The game nails the lethal radiation and gravitational lensing effects, but it takes liberties with scale. Real neutron stars are so dense that skimming their surfaces would rip any spacecraft apart long before getting close enough for those cinematic flybys. Meanwhile, Destiny 2 features a weapon called the Graviton Lance, which fires miniature neutron star projectiles. While the idea of weaponized neutron matter is pure fantasy, the gun's lore nods to real science by mentioning quantum degeneracy pressure, the very force that keeps neutron stars from collapsing further. Then there's literature. Neutron Star by Larry Niven, a classic sci-fi short story, explores tidal forces near one of these objects with terrifying accuracy. The protagonist's ship is nearly shredded by gravity's uneven pull, a real phenomenon called spaghettification, which would stretch any object into a noodle-like strand near a neutron star's surface. But even Niven's hard sci-fi takes creative shortcuts, like suggesting a human could survive such an encounter with just a reinforced ship. In reality, the tidal forces and radiation would liquefy anything within thousands of kilometers. Where pop culture truly shines is in capturing the essence of neutron stars, their otherworldly extremes. Whether it's the eerie pulsar beacons in Doctor Who or the gravitational time warps in Event Horizon, these portrayals distill real science into visceral experiences. They might exaggerate the explosions or downplay the invisible hazards, but they get one thing undeniably right. Neutron stars are the universe's ultimate forbidden zones, where the rules of physics as we know them twist into something unrecognizable. That sense of awe, at least, is 100% accurate. The real magic happens when fiction inspires deeper curiosity. A viewer might watch a neutron star in the expanse and wonder, could that really happen? That question sends them down a rabbit hole of real research, from pulsar mechanics to quark matter. In the end, pop culture's greatest gift isn't perfect accuracy. It's turning cosmic enigmas into shared stories, bridging the gap between scientific abstraction and human imagination. After all, the truth about neutron stars is already stranger than fiction. The challenge isn't making them more dramatic, but convincing audiences that reality is dramatic enough. The next decade promises to be revolutionary in our quest to unravel the secrets buried within neutron stars. With cutting-edge telescopes, gravitational wave detectors, and international collaborations pushing the boundaries of technology, we're on the cusp of breakthroughs that could rewrite textbooks. Imagine the James Webb Space Telescope's successors, like Europe's planned Athena X-ray Observatory, capturing temperature variations on neutron star surfaces with unprecedented precision. These subtle thermal fingerprints could betray the turmoil deep below, revealing whether quark matter bubbles beneath the crust or Hyperons dance in the core's depths. But it's not just about sharper images. Gravitational wave astronomy is entering a golden age. Upgraded detectors like LIGO Voyager and the future Einstein telescope will listen for collisions with such sensitivity that they could catch the moment a neutron star's core undergoes a phase transition, like neutrons dissolving into quark matter mid-collision. The echoes of these cosmic crashes might carry distortions, tiny kinks in the space-time ripple that betray exotic materials at work. And when these signals are paired with neutrino observatories like Hypercamioc, which can detect the ghostly particles fleeing these events, we'll have a multi-messenger window into processes that were pure speculation just years ago. Meanwhile, quantum computing could revolutionize how we simulate these extreme environments. Today's supercomputers struggle to model the trillion-particle chaos inside a neutron star's core, but quantum algorithms might crack the code. Researchers are already experimenting with qubit-based simulations to explore how quarks interact under neutron star pressures, a task that would take classical computers millennia. If successful, these digital laboratories could predict how strange matter forms or how magnetic fields twist in the core, giving astronomers a roadmap for what to look for in real observations. Perhaps the most exciting wildcard is the Square Kilometre Array, a radio telescope network so vast it'll scan the sky with unmatched resolution. By monitoring thousands of pulsars simultaneously, it could detect gravitational waves passing through the galaxy like ripples in a cosmic pond. These waves might subtly alter pulsar timings, creating patterns that hint at the internal structure of neutron stars light years away. It's like using the stars themselves as a giant interferometer, one that could finally answer whether quark matter exists or if hyperons soften the core. The implications stretch far beyond neutron stars. If we confirm quark matter or strange matter exists, it could explain lingering mysteries like dark matter or the universe's missing antimatter. These discoveries might even spawn new technologies, materials inspired by neutron star crusts, or energy breakthroughs from understanding superfluids that flow without friction. The next decade isn't just about solving old puzzles, it's about uncovering questions we haven't even thought to ask yet. With every new instrument, every fresh dataset, we're not just peering into a star's heart, we're glimpsing the universe's most guarded secrets, hidden in plain sight. The core of a neutron star isn't just a scientific mystery, it's a cosmic rebellion against everything we thought we knew about matter. Imagine a realm where the building blocks of reality twist into forms so alien, they make black holes seem almost mundane. We've spent decades theorizing about quark soups, hyperon dances, and strange matter hiding in these ultra-dense hearts, but the truth might be wilder than any of our predictions. What makes this quest so electrifying isn't just the answers we're chasing, it's the sheer audacity of the questions themselves. Could a neutron star's core be a portal to understanding dark matter? Might it hold clues about the universe's missing antimatter? Every hypothesis feels like stepping onto untrodden ground, where even the wrong answers could lead to revelations. Consider how far we've come already. A century ago, neutron stars were mere speculation, mathematical oddities dreamed up by theorists. Today, we've mapped their surfaces, timed their pulses, even felt their collisions ripple through space-time. Yet the core remains the ultimate locked room, hiding secrets behind walls of degenerate matter and gravity, so intense it distorts the fabric of reality. The irony, the very forces that make neutron stars so impenetrable also make them irresistible. They're not just objects to study, they're cosmic crucibles, forging states of matter that don't exist anywhere else in the universe. What's coming next could redefine physics. Gravitational wave observatories are tuning into neutron star mergers with ever greater precision, hunting for the telltale shudders of quark matter forming in the chaos. X-ray telescopes, sharper than ever, might catch the thermal whispers of a core transitioning between phases, and lurking in all that data could be the key to unifying quantum mechanics with gravity, a puzzle that's eluded Einstein's successors for generations. The stakes, nothing less than decoding the universe's deepest operating manual. But here's the real wonder. This isn't just a story for scientists. Every time a pulsar's rhythm hiccups or a magnetar unleashes a flare, it's a reminder that the universe is alive with mysteries waiting to be unraveled. You don't need a telescope to feel the thrill. Just look up at the night sky and know that somewhere out there, a city-sized sphere of pure neutronium is spinning, vibrating, maybe even cracking open under pressures we can't fathom. The next chapter of this saga isn't written yet. It might be a grad student simulation that cracks the code, or an amateur astronomer spotting an anomaly in pulsar data. Whoever solves it, one thing's certain: the truth will be stranger than we've dared to imagine, and that's why we keep